Hi everybody, this is Dr. Nadia Fuladian. This is the second part of the structures of the blood vessels, chapter 22. For some reason this part has been deleted from the video, so I'm recording that again. So far we talked about in the first part we talked about the structural differences between the arteries and veins. We talked about the big vessels that are coming out of the heart, and then all the arteries that we call them arteries. We talked about all the variation that we have, these ones in general, and now we are going to explain them more in detail, each one of them. So I'm just reviewing this picture, that the big vessels that are coming out of the heart, like the aorta and the pulmonary trunk, and the other vessels at this size, we call them elastic artery. We're going to talk about that. Then after that we have muscular artery, and then very small arteries in the body is called arteriole. We're going to talk about the structure of all these ones. Then after this we have capillaries. We have 3 types of capillaries, and we're going to talk about them. Then when the blood has come all the way to here, the exchange of the material is done in the capillaries, and then they continue back toward the heart through the venules, that they are the smallest vein. Then they are making the medium-sized vein, and then finally the large veins, and get back into the heart. So we talked about these ones a little bit on this picture, more detail. You can refer that to the video 1. Now I'm going to continue to talk about each one of these ones in more detail. So starting from the arteries, also this part I have explained a little bit in the first video. We said that the arteries by definition are the vessels that bringing the blood out of the heart. So always pay attention to this definition. We're not referring to the amount of the oxygen in any vessel to call that artery or vein. We're just talking about that is bringing the blood out of the heart or not, right? So if bringing the blood out of the heart is called artery, like pulmonary trunk is an artery and aorta is an artery, right? Now arteries, as they are coming out of the heart, then spreading the blood all over the body. So start from big arteries that we call them elastic arteries. Those are the ones that are coming directly from the heart. And as they are getting away, they get smaller and the structure is changing. Those becomes muscular arteries. Sorry about that. Then the muscular arteries branching, and finally they're making very tiny one that they cannot be seen by the by the eye. We call them artery. So we talked about the arteries for the elastic arteries, that those are the ones that are coming out of the heart directly. So first of all, for each one of these vessels that we're going to talk, you need to know the examples. Like here, aorta, brachiocephalic trunk, pulmonary trunk, these are all elastic arteries. So these elastic arteries, we want to see that what is different between elastic arteries and other types of arteries. So first of all, they have a very large size, right? The largest vessels in diameter that becomes about 2.5 centimeter. As you see, these are the biggest vessels, right? Then biggest arteries, at least we can say. Then we have the thing that makes them elastic artery, that they have the elastic membrane in the media and intima, in the internal elastic membrane and external elastic membrane, that we have discussed these ones in the wall of the arteries, and we have seen them before where they are located. So as you see, elastic arteries have both of them. As we are talking about each layer, each one of these vessels, arteries, capillaries and veins, we are going to talk about all these layers that we have discussed before, the 5 layers, and in the arteries 3 layers in the vein, and all those ones. So you need to know all of this. So as you see, elastic arteries have both of these internal and external elastic membrane, besides the 3 basic layers of the intima, media, and adventitia. Now these vessels are very resilient. It means that they tolerate pressure changes during cardiac cycle. And what does it mean? It means that when the sorry, I don't know what's wrong with me. It just happens when I start talking. Sorry for the interruption. So it was saying that the elastic arteries are very resilient, and the reason for that is that when the blood is coming out of the heart is by the push of the heart itself, right? When the ventricles are contracting, they're pushing the blood out, right? So this drive, this push pressure makes the blood go out and continue in the vessels, into the big arteries to some extent, right? But then after that, to get all the way to the end of the, for example, upper extremity or lower extremity and all those ones, it may need some help. And the big help here are these elastic arteries. Those elastic arteries have lots of elastic fiber, and those ones, they can push the blood more. So when you have an artery with the wall, when the pressure of the blood behind finishes, the wall starts getting back to the original position. And this one by itself, so if the size of the blood here, I don't have that pen with me to just draw it, just showing bit by size. Like if the size of the blood, as it is passing, the vessels dilates the vessel to this size, right? To this much. As you see, this is big here, right? As the blood passed through this part of the vessels, now this vessel is getting back to the original size it was because of the elastic fiber that it has, right? So when it happens, this returning back and elasticity, it just pushes the blood more forward, and that's the one that helps the function of the heart as a pump. Now as you see, these elastic arteries are working as a helper to the heart, and in this way they are making that, like, it's not that blood continues all the way through the vessels, not that one blood goes and like the pulse that we have, right? Is not much of the difference, and there is not much discontinuation in the flow of the blood. Now, and as here again explaining that recoil during the diastole helps propel blood forward. And as we said, the examples of these elastic arteries are aorta, pulmonary trunk, and brachiocephalic trunk, that is a branch of aorta at aortic arch. Now here you see the complete picture of the sample of the elastic arteries. As you see here, we have all 3 layers of the intima, media, and adventitia, and you see that have been shown internal elastic membrane, and also we have the external elastic membrane too, both of them, right? Then after this we have the muscular arteries. So muscular arteries, so generally the examples of muscular arteries, as you see, we have radial and ulnar, you know the location on the forearm. External carotid, for example, that goes to the outer of the head and neck. Brachial artery on the brachial area. Femoral in the thigh area, and mesenteric, that they are going inside of the abdomen. If you see, these are all and there are many more arteries in the body. Almost all of the vessels except the muscular arteries, except the elastic arteries, that those are big vessels that are coming out of the heart, around the heart, then all the other branches, after those elastic arteries are branching, all the other arteries in the body that they have a name are, most of them, as this size that we're going to talk about, that they are muscular arteries, right? So as you see, we can say as a general rule, except elastic arteries, all the named arteries are muscular arteries, right? So to see the characteristic of them, first regarding the size, as you see, these size are much less than 2.5 centimeter of those big vessels, right? No, I mean the elastic arteries. So these are medium-sized arteries, about 4.4 centimeter in diameter. They have thicker media than elastic arteries. That's an important thing, that although the elastic arteries are bigger in size, but these muscular arteries, they have thicker media, means that they have more muscle, a smooth muscle. And the vessel diameter under control of the autonomic nervous system, these are the ones that if the vasodilation is going to happen, the vessel gets dilated is by the autonomic nervous system over here, and also the same vasoconstriction that we need, that the blood gets here. Now the blood can be controlled by autonomic nervous system so that it pushes the blood more forward. And these ones also have both internal and external elastic lamina or elastic membrane. So to see the picture of that muscular artery, you see that again they have all three layers: intima, media, and adventitia. And you see the media of that is the thickest layer, that you see that here compared to the intima and adventitia. So here you see a picture of the elastic artery and compare that to the muscular artery. So you see that in the elastic artery, the elastic fibers, all of these fibers that you see, they are elastic fibers. So they make a very big portion of the vessel here, compared to the muscular artery that they have a thick muscular layer here. Now the third types of the arteries, we call them arteriole, and these are very, very small, that we call them, these are smallest arteries. Pay attention, these are not smallest vessels, because the smallest vessels are capillary. These are the smallest arteries. The size is about 30 micron in diameter. So just to remind you, a micron is 1,000th of a millimeter. So you can see millimeter by eye, but you cannot see 1,000th of millimeter by eye. So as you see, these cannot be seen by bare eye. So they have very thin adventitia, that's so thin that it cannot be we can see the whole vessel, but these ones, even under the microscopes, they are very thin. Sometimes you cannot even notice that. And media of that may be complete or incomplete. Like, I mean that not incomplete. They are not complete. The media is incomplete, means that the muscles can be seen in some parts, and on some other parts there is no muscles, right? So they are like patching all around. It's not a complete layer of the media. And these ones have only internal elastic membrane or lamina. And these are the ones that are controlling blood flow between arteries and capillaries, right? So these are the ones that can be considered as the control of the blood pressure. Like when the blood wants to pass from the big vessels, big arteries, to reach into the capillaries, they are controlling that, how much sphincter over there, how much the wall of the vessels be over there, so that the amount of the blood that passing through them. So to see the structure, that here you see that one. So these are just right before the capillary bed. These are the ones that are located right around the capillary bed here. And as you see here, you have the intima, endothelium, and basal lamina. You have some smooth muscle cells that here have been shown complete layer, but in reality is not that complete all around all the time. And you see the adventitia is so thin that it cannot be seen here. So these are the arterioles. Now after those ones we go to the capillaries. After all these arteries have brought the blood into the tissue, then at the level of all the cells that we have the capillaries. These are the smallest of all the vessels, and the diameter of them is about 8 micron compared to the 30 microns of the arterioles, right? So as you see, arterioles, they are not much bigger than the capillaries, like only 3 times, right? Or 4 times, right? But let's say 4 times. So about the diameter of a red blood cell, because the red blood cell has to pass through them, so they cannot be smaller than the size of the red blood cell. And as you have had in the blood, the size of the red blood cell is 8 micron too. And so these are the most delicate of all the vessels, and these do not have media or adventitia. Therefore, they have only intima, one thin layer, and that's completely works for the purpose that they have. The material should pass through them, so they need the thinnest thinnest possible wall that they can have, that has only one layer of the intima. And these are the only vessels of the body that nutrient and waste exchange through them between the blood and tissues, right? Now, we have 3 types of capillaries. One type is called continuous capillary, the other one is called fenestrated capillary, and the third type is called sinusoid or sinusoid capillaries. So continuous capillaries, first of all, they are the most common type of capillaries. These fenestrated and sinusoid are seen in specific areas of the body, but the most common that we have in the body is continuous. Now, let's see what's different. So one difference is in the structure. Sorry for interruption. So we're saying that these different types of capillaries, first of all, they have different location and different structure. Let's go over the structure. What is different between them, and then we can realize that why we have in specific areas of the body, we have such a specific type of capillary. So for the continuous capillaries, we call them continuous because the lining that they have is complete, right? All the cells are continuously one after another. So these are endothelial lining is complete in this. And as we said, these are the most common type of capillaries around the body. The second type, that is fenestrated capillaries, on these ones, endothelial lining is not complete. So what is not complete? Here we have some pores in the capillary lining. These capillaries have some pores in their lining, right? So pores, they are just simply some holes, right? Small holes, right? So that some bigger material can pass through them. When we have a continuous capillary, that the endothelial lining is complete, means that the cells, endothelial cells, are simple squamous cells that are attaching to each other back to back. So the material, we're going to talk about that, how the material are passing through these ones. So some of them just have to get into the cells and then on the other side get out of the cells to reach the other side. Some small material can pass between the cells and all those ones, but all this should happen for all the molecules that are going to pass, right? When we have some holes, obviously bigger molecules can pass through the holes when they cannot pass through the membrane of the cells, right? So these ones that they have hole, that we call them, so the holes are called fenestra. Therefore, these capillaries are called fenestrated capillaries. It means that they have fenestra. So this type of capillary can be seen in the places that we need. We have the more traffic of the more material are passing through the membranes, and some bigger material are passing, right? So in the mucosa of the intestinal tract, that lots of nutrients that have to pass. And in the pancreas also, so lots of material are passing through these capillaries to get into the blood. In the endocrine organs, obviously, when we need lots of material get out or in of the blood vessels, and as we said, bigger ones. And in the choroid plexus and in the ciliary process of the eye. So these are places that we have these pores in the capillaries, and we call them fenestrated capillaries. The third type of capillaries are sinusoid capillaries, that also we call them discontinuous capillaries. Compare these two ones, right? So if we say continuous, these two are continuous. This one are complete lining. These are not complete but have only pores in them. But this one are discontinuous. So discontinuous because they have big gap in the lining of the capillaries. Not only the endothelial lining is not complete, but also contain pores and large gaps in the lining. We're gonna see the pictures of all these three in the next slide. And the location that we have these sinusoid capillaries are in the liver, spleen, lymph node, bone marrow, and some endocrine glands. So these are for bigger molecules to pass through these ones. When we go to every of these organs, you see that bigger material, bigger molecules, or even sometimes cells have to pass through so that the function of that organ can be done complete. Just grabbing your attention, in your slides you may not have the locations of these ones specifically, although I may have talked about them in the previous recording that I had, but as you did not have recording, just grabbing your attention to add these ones to your slides that you have regarding the location of each types of the capillaries. Now to see the picture of them, you see that you have these three types of the capillaries. This is the continuous capillary. If you look at the wall, the intima that you have, and that's the only layer that each capillary has, that you see that you have the endothelium and the basal lamina here. So you see that they are connecting to each other back to back, and there is no hole or anything over the surface of that. And here you see that you have one cell here, you have one cell here. These are the endothelium, and this is the basement membrane of that basal lamina, and this is the lumen inside of that. And these are the continuous capillaries that are the most common type, right? Then here you have fenestrated capillary. You see that the endothelial cell, that those are the simple squamous cells that you have, they have some pores, as you see them all here. These dots that you see, these are tiny holes that we call them fenestra. The material can pass through them. And the collocation that you have here, one thing hasn't been mentioned in the previous one, that is the fenestrated capillary. We have them in the kidney too, in the glomerulus of the kidney. So it has to be added here too, because that's very important in the function of them. And as you see here, you have some, besides the space between the cells here, you have some of these holes, these fenestra here and there, that the material can pass through them too. The third type is the sinusoid ones, that you see that you have big gaps between the cells here and there, and those are the ones that the bigger molecules can pass through them. As we said, we have them in the liver, spleen, lymph node, and all those places that the bigger molecules have traffic through the endothelium. Now, for the capillaries, this is about the mechanism that they help the passage of material across the wall of the capillaries. So there are 4 ways that the material can pass between the inside and outside of the capillaries, right? In the other way, to be exchanged between the blood and the tissue around, right? So the material can diffuse across the endothelial cells, pass through the cell membrane, right? Material can diffuse through gaps between adjacent endothelial cells, right? So when we were in the epithelial tissue, these are all simple squamous epithelium. These are epithelial tissue. We talked about the epithelial tissue and all other types of the cells in the tissues that we have the junction between the cells. So the presence of those junctions determines that how much the material can pass between the cells, right? Some of the material that they cannot pass through the cell membrane, if there is an other way they can pass between the cells, right? Materials can diffuse through pores or gaps in, if it is pore, it's fenestrated capillary. If it is pore or gaps, that is the sinusoid capillary. So this is the one that gives an option to those bigger molecules. If they cannot pass through all the other way in the continuous capillaries, they can pass through the fenestrated and sinusoid capillaries. And material can move through the vesicular transport that we have discussed about that one, that when some material is made inside of the cell, they have been collected, it covered with a membrane to make a vesicle, and then transport to the wall of the cell and then pours toward the outside, right? So these are all the ways that the material can be transported through the wall of the capillaries. Now, let's talk about the capillaries and how they are working and how the blood passes through them. So first of all, capillaries are not one single layer of the vessels, like it is not arterial with the size of 30 micron comes, then the size becomes smaller, and then on the other side becomes the venule. We have a bed of capillaries, that means that we have a network of the capillaries, like a net, like if it is arterial here, then it's spreading, make a bed here, and these are, if I just show this one like this, they're continuing, and on the other side these are continuing with the venule. So we have capillary beds. So these are not individual units, they are working together. And capillaries form an interconnected network of capillaries, as we said, and the capillary bed consists of vessels connecting arterioles with venules, as I mentioned. Now we have some structures in this structure and organization of capillary bed that makes all these ones be able to connect to each other and the exchange of the material be done properly. So as the material getting here, it needs that the pressure behind the blood be proper enough so that the material have time over there to get out of this capillary, to get into the tissue around, or those material from the tissue that are excess over there, like the waste material, carbon dioxide, whatever is in higher concentration, get into the capillary and continue its way toward the venule. So let's look at with a closer look at capillary structure. So these are the ones that we have over there. Arteriovenous anastomosis. So anastomosis is a connection, right? When these two are connecting to each other, not through the capillaries, right? Through another vessel. So we call that vessel as anastomosis. As we have them between arteriole and venule, that we call him arteriovenous anastomosis. The other one, we have some channels, we call them thoroughfare channels. Thoroughfare channels. And another one that we call it mid-arteriole. So we are going to see the location of all these ones, and also pay attention that contracting and relaxing smooth muscles of these location that I'm going to show you, they are determining the blood flow. If the blood has to slow down over there, right? So we have some places that act like a sphincter, so that the less blood or more blood can pass through them, depending on if they are relaxing or contracting, right? So here you see the picture of the capillary bed. Like the whole this area is the capillary bed that are working together, so that the material that are coming from the arterial side, they go into the capillaries and then go into the venous side and continue back their way to get back toward the heart, right? Now, as you see, they are in form of a network, right? Now you see that at the beginning of each bed of the capillary, you have the sphincter structure. As you look at the smooth muscles around the wall that you have on these parts, you see that we call them pericapillary sphincters. So these smooth muscle cells act as an sphincter, so that when they contract, make less blood pass through them. When they relax, makes more blood pass through them, and in this way control the amount of the blood that go into the capillary. Sometimes we need the blood remains inside of those bigger vessels and continue their way, so that keep the circulation the whole body, right? Therefore less blood goes here. Sometimes we need more exchange of the material be done in this area, therefore more blood gets into this capillary bed, so that it can be exchanged with this one. And as you see, these pericapillary sphincter, it might be in many different levels around this capillary bed, and these are all smooth muscles that we have over. The other things that you see here, you see that we have some way in some organs, we have some direct ways that blood doesn't have to pass through all the capillaries to go into the venule side. It just passes through inside the bed of these capillaries that gets toward the other side fast, right? We call these ones, these are channels in the middle, that we call them thoroughfare channels. And in some areas of the body, like for example in the brain, heart, stomach, and some other organs, then we need a continuous rich flow of the blood. Therefore, in those areas, like you have seen many of the blood vessels, or you will see, and then you know that, for example, in the brain we have circle of Willis, right? So we have so many vessels that they are supplying to a specific area of the body, right? So more than one artery is supplying a specific area, right? And for the reason for that is that if one of those artery blocked, or for any reason blood cannot reach that area, the blood can reach to that area through another vessel. So in general, we have a term, we call it anastomosis. Anastomosis is referring when two vessels are connecting to each other, right? So first we are talking about the collateral arteries. Collateral arteries are the arteries that are separating from each other and go alongside each other, lateral to each other, to supply around one area through two vessels. So we call those ones collateral arteries. And on the other hand, most of the time at the very end, they are connecting to each other. Even if they have come from different places, when they are connecting to each other, we call that connection anastomosis. And as here we are talking about the arteries that are bringing the blood, oxygen and nutrient to a specific area, that ones are arterial anastomosis, like the ones that we have in the circle of Willis in the brain, right? And you will see other examples of that, or when we go over the blood vessels of the body, you will see that we have some arterial anastomosis through the arteries, right? And the reason, as we said, is that when arterial is blood, then the other ones can supply the capillary bed in that area. Now, in some areas of the body, like for example in the joints, that there are lots of movement, and if the blood is passing, like if it is a knee joint here, imagine this is the knee here, the blood is pass here and continue its way to the rest, right? If this knee is bending, then it may interrupt passing of the blood flow completely, right? In those areas also we have a kind of network of the vessels in that area. And in those ones, so that the body movement do not interrupt the circulation to the afterward parts of the body. And in order to accommodate this, there must be a direct connection between arterioles and venules, and these are the ones that we call them arteriovenous anastomosis, and those are the ones that you see in this picture here as this one, arteriovenous, between the arteriole and venule, right? The direct connection, so that if the other areas blood cannot pass, at least blood can pass through these ones and go over there. And as we know, those movements don't last long, right? Just after a while you move that part of that body, but the blood get back over the other area that is needed, but at least this one prevent so that the movement of the blood to the rest of the body and to continuation of the blood back to the heart be interrupted, right? Then the other thing is that in some of the connective tissues we have thoroughfare channels that connect arteriole with venule, as we said, and also we have another term for capillary sphincters in some areas, for example in the mesenteries that we have inside of the abdomen, and we call those ones, those pericapillary sphincters, we call them as metarterial. So metarterial are exactly the precapillary sphincters in some areas of the body that they guard the entrance to the capillaries, as we discussed. And as we said, these are contain smooth muscles, as the one that you can see here. Thoroughfare channels are here, and these ones that can be called metarterial in the mesentery. So that's the end of this part, so you can continue the rest for the vein in the next video. Have a good time.